Swayam Prabha. Digital India. Educated India.
Now let us start with the matrices. So I hope all of you know about what is matrix. Matrix is an operator. Define matrix. Matrix is a rectangular array arranged in rows and columns. That is the difference between define and what is matrix. Now let us start with the definition of matrices. With m comma n belongs to capital N, a real valued m comma n, m rows and n column matrix A is an mn tuple of elements A I j, where I equal to 1 to m and j equal to 1 to n, which is ordered according to rectangular scheme consisting of m rows and n columns. That is, A can be represented as A11 first row first column, A12 first row second column, A12, A13 and so on, A1n, and A21, A22, A2n and so on, AM1, AM2 and so on, AMN, where Aij belongs to R. So by convention, 1 comma n matrices are called rows and m comma 1 matrices are called column. These special matrices are also called rows by column vectors. So this matrix addition and multiplication, let us go to discuss. Now we can represent in terms of the vector, long vector A, right? A belongs to R power 4 cross 2, mean 4 rows, 2 column. So 1, 2, 3, 4, 4 rows and 2 column, 1 and 2. Similarly, A in R power n mean 1 column, and then we can represent like this. So the sum of two matrices A belongs to m rows and n column and B belongs to m rows and n column is defined as element. Then we can what sum of these two matrices A plus B is equal to A11 plus B11, that is corresponding entry I have to add A12 plus B12 and so on, A1n plus B1n. Similarly, AM1 plus BM1 and so on, AMN plus BMN, where this matrix belongs to m rows and n column. So for the matrices A belongs to R power m cross n and B belongs to R power n cross k, the element Cij of the product C is equal to AB belongs to R power m cross k are computed as Cij is equal to summation I equal to 1 to n Aij Bij, where I varies from 1 to m and j varies from 1 to k, or the matrix representation in the general notation. So this means to compute the element Cij, we multiply the elements of the ith row of A with the jth column of B and the sum up later in the notation of this. We will call this as the dot product of the corresponding rows and column. In cases where we need to be explicit that we are performing the multiplication, and we use A dot B mean product of two matrices and denoted the multiplication, and explicitly the showing the dot represent the product of the two matrices. That is the meaning of this. So we have a note, matrices can only be multiplied by if their neighboring dimensions match. For instance, n cross k matrices, A can be multiplied with k cross m matrices, but only from the left side. See, the first matrix of the column, second matrix of the row are equal, then only the matrix multiplication exists. So that the resultant will be n cross m. Therefore, the product BA is not defined if m is not equal to A. since the neighboring dimension do not match. Therefore, carefully do that. First matrix of the column and second matrix of the row where length value is same, then matrix multiplication exists. Next remark is the matrix multiplication is not defined as an element wise operation on matrix elements, that is Cij not equal to Aij into Bij, even if the size of the A and B was chosen approximately or appropriately. So, this kind of element wise multiplication often appears in programming languages when we multiply multi-dimensional arrays with each other and is called, this is the Hadamard product. Now, let us start with an example. You take a matrix A, 1, 2, 3, 3, 2, 1 means 2 rows and 3 columns belongs to R power 2 cross 3 and B equal to 0, 2, 1, minus 1, 0, 1 which belongs to 3 cross 2 we obtain. AB is equal to what? Product them. Product what happened? So, written like this A and B, first this into this you multiply so that you can get the value of 2 and this into this you multiply, you get the value of 3 and second row into first column you multiply, you can get it the value of 2 and second row multiply with the second column you have 5. Now, so first one is, this one is 2 cross 3, second one is 3 cross 2, therefore, the net value is 2 cross 2. So, that is a what matrix multiplication exists, that is the meaning of 2.15. BA you take other way. So, what is BA? BA is 3 cross 2. What is A? A is nothing but what 2 cross 3. So, these two are equal, therefore, matrix multiplication exists. So, we have a 3 cross 3 is 3 rows and 3 columns. Therefore, this is the same technique we apply it. Therefore, 2.16 you can get the solution to the problem. So, this is the way we can do the multiplication of two matrices. Now, we have identity matrix. You have a n rows and n column. We define the identity matrix as In equal to, so main diagonal you take it. So, this value is 1, rest of the diagonal is 0, above and below diagonal is 0. That is the meaning of identity matrix of n cross n matrix. So, it follows the following properties. One is associativity. Associativity is a meaning of 3 values required. One is A matrix, another one is a B matrix, third one is a C matrix. If you multiply with AB into C, which is equal to what? A into BC. So, that is the meaning of associativity. So, AB into C, which is equal to A into BC. Next one is distributivity, that is you take for all A comma B in R power m cross n and then C comma D belongs to R power n cross P. Therefore, A plus B into C equal to AC plus BC and A into C plus D equal to AC plus AD. So, that is the meaning of distributive property. Next one is a multiplication with the identity matrix where A belongs to R power m cross n. Therefore, identity into A is equal to AI into IN equal to A. Therefore, note that I m mean m rows and m column is not equal to n rows and n column of the identity matrix. That is I2 and I3 are not equal. So, that is the meaning of general form of the identity matrices. Next, inverse and transpose. So, inverse matrix is, consider a square matrix A in R power n cross n. Let the matrix B belongs to R that is n rows and n column, have the property that AB is equal to IN, which is equal to BA. Therefore, B is called the inverse of A and is denoted by A inverse. So, note that existence of inverse of 2 cross 2 matrix, consider the matrix A11, A12, A21, A22, which belongs to R. R is 2 rows and 2 column. If we multiply A with A dash is inverse matrix, that is you have to change the main diagonal, that is A22, A11, and change the sign of the opposite diagonal, minus A1 minus A2, that is the meaning of inverse of the matrix. And also you have to find the determinant of A. So, determinant of A is not equal to 0, then only inverse exists, we can proceed further. Now, you multiply A and A dash, A inverse. Now, it should be identity matrix comes, then the existence of inverse exists. So, for simply you multiply them. So, this is the first row of the first matrix, multiply with the first column of the second matrix, you have the values, and here 0 0 will come, here this value will come, identity will come, then A inverse is like this. If and only if this value is not equal to 0, so in this section we see the matrix multiplication exists or not, that we can find out, and then further we can generally use the determinant to check whether the matrix is invertible. Next, inverse matrix. So, inverse matrix is you take a matrix A, for example, you take a 3 cross 3 matrix, 3 rows and 3 columns, and B is another matrix, 3 rows and 3 columns. If you say A and B are inverse of the one another, multiply them, the resultant I will come, then one is the inverse of the other matrix. So, here these two matrices are multiplying and we have identity comes, therefore, definitely these two are inverse of the one another, implies A into B equal to I equal to BA. So, in that case only what the inverse matrix is, and we have a commutative. Next definition is a transpose. Transpose is nothing but change rows to the column, column to the rows. So, let A in R power m cross n be the matrix and B in R power n cross m with another matrix. So, if Bij and Aji are equal is called transpose of A, we write B equal to A transpose. In general, A transpose can be obtained by writing the column of A as the rows of A transpose. The following the important properties of the inverses and transposes exist. Suppose you take a matrix A of n cross n and A inverse is what inverse of A, multiply them, identity comes, and then definitely the A inverse into A is also exists. So, this is the properties of what inverse matrix exists. Another is if you take A matrix and B matrix, multiply them, find the inverse, and then the resultant is B inverse into A inverse. And third one is if you take two matrices A and B, add them, find the inverse. So, it is definitely not equal to individual of inverses, that is A inverse plus B inverse, separately do that and add them and then find the inverse, definitely they are not equal to one another. And then 2.29 says that take a matrix A and transpose the whole transpose, you take it, so that what A transpose the whole transpose is A. Next, AB whole transpose is nothing but B transpose into A transpose, and addition of these two matrices can be splitted into sum of their matrices of the transpose. So, that is also true. Okay. So, carefully do that inverse and transpose. For the transpose, addition of two matrices, take the transpose and independently they can split up. Whereas, if you take two matrices A and B, add them, inverse find out, definitely they are not equal to their independent inverses. So, that is the inference you have to learn from the properties of what? Inverse and transpose of the matrix. Next is symmetry matrix. The symmetric matrix in the sense that you take a matrix A which belongs to R power n cross n is a symmetric if A and A transpose are equal. Mean you take a matrix A and convert to rows to the column, then column to the rows, and check it out. If they are equal, then the matrix is said to be symmetric matrix. Note that n rows and n column matrix can be symmetric. Generally, we call n by n matrices also a square matrices because they possess the same number of rows and column. Moreover, if A is invertible, then so A transpose is also invertible, and A transpose is the thing, but A inverse the whole transpose equal to A transpose the whole inverse, which is equal to A minus transpose. So, this is the meaning of what? Matrices as a symmetric matrix. Now, we have a note, that is, you take a two symmetric matrix, sum and product. The sum of the symmetric matrices A and B belongs to R, that is R is n cross n, n rows and n column is always symmetry. However, their product is always defined, it is generally not symmetric. Suppose you take a matrix 1 0 0 1, 1 1 you take it, now product them, but these two independently symmetric, but if they product them, the resultant is 1 1 0 0, it is not a symmetric. Therefore, carefully do that. If A and B are symmetric and if you multiply them, it not necessarily come, it should be symmetric. Next, multiplication by a scalar. Let us look what happens to matrices when they are multiplied by a scalar lambda in R. Let A belongs to m rows and n column, and lambda is a real number R, then lambda A equal to k and kij equal to lambda into aij. Practically, lambda scales each element of A and lambda comma psi in R, the following holds. First, it is associativity, that is, you take a scalar lambda and psi is also a scalar and multiply them with matrices C, then these two scalar can be written as lambda into psi into C, where C belongs to m rows and n column. Another one is take a scalar lambda, multiply with the two matrices B and C, and then we can split it into lambda B into C, which is equal to B into lambda C, which is equal to BC into lambda. Therefore, B belongs to what? M rows and n column, C belongs to n rows and n column, then only the matrix multiplication exists, we can do the properties of these scalar ideas. So, note that this allows to move the scalar values around. Similarly, next one is lambda C whole transpose can be written as C transpose lambda transpose. Lambda is a scalar, take the transpose, lambda only will come because it is a scalar, and then C transpose lambda equal to lambda into C transpose. Since lambda and lambda transpose are equal, therefore, it is holds good. Next, distributivity, lambda plus psi into C, which is equal to lambda C plus psi C, where C belongs to R power m cross n, and lambda into B plus C equal to lambda B plus lambda C, and B comma C belongs to R power m cross n. So, that is the meaning of what? Distributivity ideas. Next, you take an example, one C is a matrix of 2 cross 2, 1, 2, 3, 4 is a one matrix. Then for any lambda comma psi in R, we obtain lambda plus psi into C is equal to lambda plus psi into 1, lambda plus psi into 2, lambda plus psi into 3, lambda plus psi into 4. So, all elements you have to multiply with lambda plus psi. Now, for first row first column lambda plus psi, into 1 is lambda plus psi. For second row, first row second column 2 lambda plus 2 psi. For second row first column is 3 lambda plus 3 psi, and for second row second column 4 lambda plus 4 psi. Therefore, you can split it into two different matrices. One is lambda 3 lambda 2 lambda, another one 4 lambda, another one is psi separate, psi 2 psi 3 psi and 4 psi. Now you see that it is lambda into c, lambda can take it all common to all, and then psi can take it all. Therefore, lambda c plus psi c will come. So, this way we can use the distributive property in terms of the scalar. Next, compact representation of a system of linear equations. If we consider the system of linear equation 2x1 plus 3x2 plus 5x3 equal to 1 and 4x1 plus minus 2x2 minus 7x3 equal to 8, 9x1 plus 5x2 minus 3x3 equal to 2, and use the rules for matrix multiplication. So, we can write the equation in a more compact way as coefficient of x1, x2, x3, you take it, the first one is 2, 3, 5, second one is 4, minus 2, minus 7, third one is 9, plus 5, minus 3, and we have an unknown variable x1, x2, x3, so which is equal to 1, 8, 2. Now, you see that x1 scales the first column and x2 is the second column and x3 is the third one. So, we represent this system to the matrices. Now, you can easily solve the problem. Now, solving system of linear equation. So, we introduce the general form of the equation of the system, that is a11 x1 and so on a1n xn equal to b1, and am1 x1 and so on amn into xn equal to bm. Now, where aij belongs to R and bi belongs to R is known as constant, xj are unknowns. Therefore, where I varies from 1 to m, j varies from 1 to n. So, we saw the matrices can be used as a compact way of formulating systems of linear equations, so that we can write Ax equal to b and see the example of 2.10. Moreover, we define a basic matrix operation such as addition and multiplication of a matrices. In the following, we will focus on solving the system of linear equation and provide an algorithm for finding the inverse of a matrix. So, next one is a particular and general solution of the system. Before discussing how to generally solve the system of linear equation, let us have a look at an example. Consider the system of equation, that is 2 rows and 4 columns, multiply with x1, x2, x3, that is 2 unknown equation, 4 unknown variable, 2 equation, and we have a 42, 8 is a right hand side. The system has a 2 equation and 4 unknowns. So, in generally we would expect to infinitely many solutions. This system of equation is in a particular easy form, where the first 2 columns consists of a 1 and 0. Remember that we want to find a scalars x1, x2, x3, x4 such that the summation of this is equal to b, where we define C I to be the ith column of the matrix and b be the right hand side of this. So, a solution to the problem can be found immediately by taking 42 times the first column and 8 times the second column, so that b equal to 42, 8 equal to 42 into 1 comma 0 plus 8 into 0 comma 1. Now, therefore, a solution is 42 comma 8 comma 0 0. So, this solution is called a particular solution or special solution. However, this is not the only solution of this system of linear equation. To capture all the other solutions, we need to be creative in generating 0 in the non-trivial way using the columns of the matrix. Adding 0 to our special solution does not change the special solution. To do so, we express the third column using the first 2 columns, which are of this very simple form. 8 comma 2 can be written as 8 into 1 comma 0 plus 2 into 0 comma 1. So that 0 is equal to 8C1 plus 2C2 minus 1C3 plus 0C4. Therefore, x1, x2, x3, x4 equal to 8, 2, minus 1, 0. In fact, the scaling of this solution lambda in R is a product of a 0 vector, that is two system of the linear equation 1, 0, 8, minus 4, 0, 1, 2 into 12 can be written as lambda times of this, which is equal to lambda 1 into 8C1 plus 2C2 minus C3 equal to 0. So, this way we can express the what? The system of linear equation. Following the same line of the reasoning, we express the fourth column of the matrix in 2.38 using the first two columns and generate another set of the non-trivial versions of 0 as 1, 0, 8, minus 4 and 0, 1, 2, 12 into lambda 2 into minus 4, 12, 0, minus 1. We have what? Lambda 2 into minus 4C1 plus 12C2 minus C4 equal to 0. So, for any lambda 2 in R, putting everything together, we obtained all solution of the equation of the system, which is called general solution, as the set X belongs to 4 tuple. Therefore, X can be expressed as 42, 8, 0, 0 plus lambda 1 times of 8, 2, minus 1, 0 plus lambda 2 of minus 4, 12, 0, minus 1, where lambda 1, lambda 2 belongs to R. So, we have a note. The general approach we followed consists of the following 3 steps: find a particular solution to Ax equal to B, find all solution of Ax equal to 0, and combine the solution from step 1 and step 2, we get the general solution. So, neither the general nor the particular solution is unique. Next, elementary transformation. Exchange of 2 rows or 2 equations also we can do. The rows in the matrix representing the system of the equation, that is the first step. Next step, multiplication of an equation, either row or column, with a constant lambda in R, negation 0, addition of 2 equation also allowed. So, this is the technique you have to apply in the elementary transformation. For example, you take an element A in R, we seek all the solution of the following system of equations: minus 2x1 plus 4x2 plus minus 2x3 minus x4 plus 4xy equal to minus 3. Another equation 4x1 minus 8x2 plus 3x3 minus 3x4 plus xy equal to 2. Another equation x1 minus 2x2 plus x3 minus x4 plus xy equal to 0. And the last equation x1 minus 2x2 minus 3x4 plus 4xy equal to E. So, that equation represents 2.44. Now, we have to determine the value of A. We start by converting the system of the equation into compact matrix notation Ax equal to B. We no longer mention the variables x explicitly and build the augmented matrix in the form of A comma A slash B, in the sense that right hand side also bring to the given matrix. This is called it as augmented matrix. So, the coefficient of x1, x2, x3, x4, xy of the first equation, you take it into first row and corresponding value is minus 3. Similarly, for second row, 4, minus 8, 3, minus 3, 1 and right hand side value 2, and third one is 1, minus 2, 1, minus 1, 1, corresponding value of the right hand side is 0, and the last equation 1, minus 2, 0, minus 3, 4 and the corresponding value is A. So, this way you have to take it into account of converting the augmented matrix from the given system of linear equation. So, where we use to vertical line to separate the left hand side from the right hand side. So, we use this operation to indicate the transformation of the augmented matrix using the elementary transformation. Now, we have to swap rows 1 and 3, so that we have the equation. After that, multiply the R1 into minus 4 and plus 2 into R1, and last row minus R1. So, like that you have to do so that the resultant will come. Now, we apply the indicating transformation, subtract rho 1 4 times from rho 2, and then we obtain what? R minus R1 minus R3 of the last equation, you can get it. Similarly, for second step, right, after this you take it into second row with minus 1, you can get it, and minus 1 by 3 you have to get it. So, you get the value of the matrix, and similarly you also do the argument of the same, so that you can get the what below diagonal everything will be 0, right, and above diagonal we have the entry, so that we can easily apply the solution to the problem by direct substitution, like the see x1 minus 2x2 plus x3 minus x4 plus x5 equal to 0, and second matrix, second row is the equation x3 minus x4 plus 3x5 equal to minus 2, and third equation is x4 minus 2x5 equal to 1, and the last 0 equal to a plus 1. Therefore, a may get the value of a plus 1 equal to 0, therefore, a equal to minus 1. This system can be solved. Therefore, a particular solution of this system is x1, x2, x3, x4, x5 is 2, 0, minus 1, 1, 0. So, the general solution which capture the what? The set of all possible solution is x belongs to R power 5, where x equal to these values. So, this way we can represent x in terms of what? The matrices. Next, we have a row echelon form. A matrix in a row echelon form, if all rows that contain only zeros are at the bottom of the matrix, correspondingly all the rows that contain at least one non-zero element are on the top of the rows that contain only zeros. That is the meaning of row echelon. So, looking at non-zero rows only, the first non-zero numbers form the left, also called the pivot or the leading coefficient, is always strictly to the right of the pivot of the row above it. Note, basic and free variables. The variables corresponding to the pivot in the row echelon form are called basic variables, and the other variables are free variables. For example, this point 2.45 x1, x2, x3, x4 are a basic variable, whereas x2, x5 are free variables. Another note is, obtaining a particular solution, the row echelon form makes our lives easier, where we need to determine. So, the row echelon form makes our lives easier when we need to determine a particular solution. To do this, we express the right hand side of the equation system using the pivot column such that b equal to summation I equal to 1 to p lambda I pi, where pi I varies from 1 to p or the pivot column, and lambda I are determined easiest if we start with the rightmost pivot column and work our way to the left. And in the previous example, we would try to find lambda 1, lambda 2, lambda 3, so that lambda 1 into 1 0 0 0 plus lambda 2 into 1 1 0 0 plus lambda 3 into minus 1 1 0, which is equal to 0 minus 2 1 0. From here, we find relatively directly that lambda 3 equal to 1 and lambda 2 equal to minus 1, lambda 1 equal to 2. When we put everything together, we must not forget the non-pivot column, for which we set the coefficient implicit to 0. Therefore, we get the particular solution is x equal to 2 0 minus 1 1 0. So, further note, reduced row echelon form, and equation system is in reduced row echelon form, also row reduced echelon form or row canonical form. If it is in row echelon form, every pivot is 1, the pivot is only non-zero entry in its column. So, next to note is, using this we can apply with the Gauss elimination, is an algorithm that performs elementary transformation to bring the system of linear equation into reduced echelon form. Another example, row reduced echelon form, verify that the following matrix is reduced to row echelon form. The pivots are in bold. So, that is 1, 1, 1 pivoted and 1, 3, 0, 0, 3, 0, 0, 1, 1, 1, 0, 9, 0, 0, 0, 1, minus 4. So, the key idea for finding all the solution Ax equal to 0 is to look at the non-pivot columns, which we will need to express as a linear combination of the pivot column. The reduced row echelon form makes this relatively straightforward, and we express the non-pivot column in terms of the sums and multiples of the pivot columns that are on the left. The second column in 3 times the first column. So, we can ignore the pivot column on the right of the second column. Therefore, to obtain 0, we need to subtract the second column from the 3 times of the first column. Now, we look at the fifth column, which is our second non-pivot column. The fifth column can be expressed as 3 times the first pivot column. So, 9 times the second pivot column and minus 4 times the third pivot column. So, we need to keep track of the indices of the pivot columns, and translate this into 3 times of the first column. So, 0 times the second column, which is non-pivot column. So, 9 times of the third column, which is our second pivot column, minus 4 times the fourth column, which is the third pivot column. So, then we need to subtract the fifth column to obtain 0. In the end, we are still solving the non-homogeneous equation system. So, the summarize all the solution of Ax equal to 0, where x belongs to R power 5 are given x in fifth tuple. X can be expressed lambda 1 times of 3 minus 1 0 0 0 plus lambda 2 into 3 0 9 minus 4 minus 1, where lambda 1 lambda 2 belongs to R. Now, we will go to the minus 1 track. In the following, we introduce a practical trick of reading out the solutions x of the homogeneous system of linear equation Ax equal to 0, where A belongs to R power k cross n, where x belongs to R power n. To start, we assume that A is the reduced to row echelon form without any rows that just contain zeros. That is, A can be expressed as 0 0 0 1 and 0 0 like that. Second row, we have 1 introduced here and last one introduced. So, this is a trick we have to do that, and then where star can be arbitrarily real numbers, which with the constraints that the first non-zero entry per row must be 1 and all other entries in the corresponding column must be 0. Therefore, the columns J1, J2 and so on Jk with the pivots marked in the bold are the standard unit vectors E1, E2 and so on Ek in R power k. So, we extend this matrix to an n cross n matrix A by adding n minus k rows of the form. So, we have like this, so that the diagonal of the argument matrix A containing either 1 or minus 1, then the column of A contains minus 1 as a pivot or the solution of the homogeneous system of equation Ax equal to 0. So, to be more precise, and these columns form a basis and of the space of the Ax equal to 0, which we will later call the kernel of the null space. Next, minus 1 trick, in the sense that let us revisit the matrix of 2.49, which is already reduced to REF and row reduced matrix of A equal to 1 3 0 0 3 0 0 1 0 9 0 0 0 1 minus 4. We now augment with this matrix to 5 cross 5 matrix by adding rows of the form 2.52 at the places where the pivots of the diagonals are missing and obtain A tilde represent 1 3 0 0 3 and 0 minus 1 0 0 0, that is we introduce, and 0 0 1 like that, and 0 0 0 as it is, and 0 0 0 0 minus 1 as our assumption to do that, so that we can get 5 cross 5. From this form, we can immediately read out the solution Ax equal to 0 by taking the column A tilde which contain minus 1 on the diagonal. So, x belongs to r power 5 and then x equal to lambda 1 into 3 minus 1 0 0 0 plus lambda 2 equal to 0 3 0 9 minus 4 minus 1. So, which is the identical to the solution of 2.50, then we obtain by the insight that we can easily calculate. Now, calculating the inverse, to compute the inverse A inverse of A inverse of A R belongs to n cross n, we need the following matrix X that satisfy Ax equal to I, then x equal to A inverse we can write down as the set of simultaneous linear equations Ax equal to I, where we solve for x equal to x1 and so on xn. We use the augmented matrix notation for the compact representation of the set of the system of linear equation A bar in and so on in bar of A inverse. So, this is augmented matrix we can convert. Now, this means that if we bring the augmented equation system into reduced row echelon form, we can read out the inverse of the right hand side of the equation system. Hence, determining the inverse of the matrix is equivalently to solving the system of linear equation. Now, another example, calculating an inverse matrix by Gaussian elimination to determine the inverse of A 1 0 2 0 1 1 0 0 1 2 0 1 1 1 1 1. Now, we write down the augmented matrix like that, and right hand side you have to write after the cross unit matrix you have to write, and use the Gauss elimination to bring into the reduced row echelon, that is R1 subtract R2 and so on. So, right hand side you have to bring identity matrix, and then after row reduce you have the matrix like that. So, this is called as inverse of the matrix. So, A inverse equal to minus 1 2 minus 2 2 1 minus 1 2 minus 2 1 minus 1 1 minus 1 minus 1 0 minus 1 2. So, we can verify that 2.58 is the indeed the inverse by performing the multiplication of A inverse and observing that we recover I4. So, we can easily find the inverse of the matrix with the help of the Gauss elimination. Now, for algorithms for solving the system of linear equation is a special cases, we may able to determine the inverse A inverse such that the solution of Ax equal to B is given as x equal to A inverse B. However, this is only possible if A is a square matrix and invertible, which is often not the case. Otherwise, under mild assumption A needs to have linearly independent column, we can use the transformation Ax equal to B and A transpose Ax equal to A transpose into B. Therefore, x equal to A transpose A the whole inverse into A transpose B. So, and using the Moore-Penrose pseudo inverse, A transpose A whole transpose inverse is A transpose to determine the solution that solve Ax equal to B. So, which also corresponding to the minimum norm least square solution. A disadvantage of this approach is that it requires a many computation for the matrix product and computing the inverse of A transpose A. Moreover, for reasons of numerical precision, it is generally not recommended to compute the inverse of pseudo inverse. In the following, we therefore briefly discuss alternative approaches to solve the system of linear equations. In practice, the system of many linear equations are solved indirectly by either stationary iterative method such as Richardson method, Jacobi method, Gauss-Seidel method, successive over relaxation method, Krylov subspace methods such as conjugate gradient, generalized minimal residual or biconjugate gradient. So, we refer to the books of Storr and Berlish, Strange and Leeson and Megerman for further details, so that you can understand the depth of this above technique. And let x star be the solution of Ax equal to B. The key idea of these iterative methods is to set up an iteration of the form x power k plus 1 equal to c into x power k plus d for suitable c and d that reduces to residual error of the norm of x power k plus 1 minus x star in every iteration and converges to X star, we will introduce the norm which allows the compute the similarity between the vectors in the section. So, that is the meaning of system of linear equation using the indirect method of the techniques.